Began our journey into magnetism. Magnetism is a super interesting force that lays at the heart of so much technology that we use today. And just as we begin, I'm going to try to teach these things without electronically, which means I'm not there to help you with things like right-hand roll, left-hand roll. I'm happy if you're having any trouble. I'm happy to try to set up a FaceTime or something to kind of help you with that if you're having challenges with it. But hopefully these notes will be enough. Please be patient with me as we go through and make sure you're practicing as we go along to make sure you can get the same answers for the problems that we're doing. We're going to start by talking about the difference between an electric force and field and a magnetic force and field. So we're very used to electric forces, and when you have an electric force, it's kind of nice. If I have an electric field, and I place a positive charge in it, I know my positive charge is going to experience a force in that direction. If I have a negative charge, I know my negative charge is going to experience a force that is anti-parallel to the direction of the field. This is very different than magnetism, because with magnetism, when you have a field, let's say you have a B field pointed this way, your force can be a lot of different directions, but your force always has to be perpendicular. So your force has to be something that is perpendicular to your B field, and is generally always perpendicular to your velocity vector as well. So that's a big difference. Our magnetic force is never going to be in the same direction as our magnetic field. This is because of the unique properties of a cross product. So magnetic force is, by definition, QV cross with B. So when you take a look at this, we talked about how to do cross products in the fall. So if you need to, you might want to review your notes on that. But if you remember, when we do a cross product, we do I hat, we have a determinant, I hat, J hat, K hat, and then we do the components. So the X, Y, and Z component of V, and the X, Y, and Z component of B. In addition, this is pretty useful, you can also use the shortcut. Now this will not give you the direction, this will only give you the magnitude, that the magnetic force is the magnitude of QV, the magnitude of B, times sine of the angle between those two vectors. So sine of the angle between V and B. Now, if we have to find directions, what we can do is use something called a right-hand rule. If we know we have a positive charge, so if we have a positive charge, we're always going to use the right hand. If we have a negative charge, we're going to do the exact same thing. We're going to use the left-hand rule. There's two approaches that I'm going to teach you. One is called the pistol rule, and the other one is called the palm rule. So depending on your teacher that you had for magnetism last year, you may have learned the pistol rule or the palm rule. I'm going to take you through both of them just to explain. With the pistol rule, your magnetic force is going to be represented by your thumb. Sometimes when I'm doing problems like this, I just write F on my thumb. And your moving charge, which can be your current or your velocity, is represented by your index finger. So this is my thumb, this is my index finger, and my magnetic field lines, my B, represented by my bird finger. So what's really important when you do this with the pistol rule is all three fingers have to be perpendicular to each other. So you have to hold them perpendicular to each other so you can solve the problem. So you're making a nice pistol with your hand when you're using it. With the palm rule, very similar, except now your thumb is going to be your velocity, and then your magnetic field is going to be the direction of your fingers, and your force is going to be your palm. So whichever rule you prefer, you can feel free to use it, but we're going to use it to do some problems together in the next part. Okay, so let's work on this together. At this point, it's advisable to pause the video and try the first four and see if you can get the right answers. Just a reminder, when we talk about X's and dots, X's mean into the paper, that's from the previous PowerPoint, and dots mean out of the paper. So that means your vector is coming out of the paper. So now let's go through what you would get in this case. So in this case, I have a velocity vector and I have a magnetic field vector, but our formula says that those two vectors, the V vector and the B vector, are in the same direction. So when you take the magnitude of QV times B times sine of the angle, you're going to find out the angle between them is 0, which means the force is going to be 0. So there is no force in number 1. In number 2, now we're just looking for the direction. You're going to take, since it's a positive charge, you're going to use your right hand rule, so RHR, whichever rule you use. So I am using the pistol rule, so I put my index finger in the direction of the velocity, and I rotate my bird finger in the direction of the magnetic field, which leaves my force finger, my thumb, going in to the paper. So the answer for this one, velocity, bird finger, and your thumb is into the paper, so that's the direction, is into the paper, so we can write it as X. Now the next part, you have current. Again, current, we know by convention is positive charge flowing, so we're going to use our right hand rule. So we take our index finger in the direction of current, we rotate, keeping everything perpendicular, we rotate it so our bird finger is in the direction of the magnetic field, and now my thumb, which is my force finger, is out of the paper. Okay, last but not least, we have a magnetic field that is going to the left, and we have a negative charge which is into the paper. Right away, we recognize it's negative, so I have to go to my left-hand rule. So my velocity is into the paper, so I point my index finger into the paper, and then I rotate my bird finger so I have to rotate my wrist a little bit. I rotate my bird finger so that it's going to the left, and that leaves my thumb pointed south. So I'm going to write down that my force on this particular one is going south, or you could also write down 270 degrees. I would be careful with the terms up and down, because typically when we say up out of the paper and into the paper, that's actually up and down. Continuing along with this, we are going to take a look at a positive charge that's moving to the right. That positive charge has a velocity that's v, and you're going to take your index finger to the right, rotate your wrist so that your bird finger is out of the paper, which means I've got a force that's pointing down. So just double check that that's correct. So my force is going to be coming out of the paper. For number 6, this is going to be a little bit different. You're going to have your current, again, this is also right-hand rule. So number 5 was right-hand rule, and number 6 is also going to be right-hand rule. So you're going to take your index finger going in the direction of current. You're going to rotate your wrist so that your bird finger is into the paper, and your thumb is actually going to be pointed this way. So that's the direction of my force. So if you want to write down a direction, you could say 135 degrees. You could say north. Probably the easiest thing is just to say northwest. Last two. Here we go. Number 7 and number 8. I have my index finger coming out of the paper. I know it's positive charge, so I'm going to use my right hand rule. So I'm going to have my index finger out of the paper. My bird finger is pointed to the right, and my force, my thumb, is pointed at 270 degrees or south. Again, avoid the term down, because down tends to mean into the paper. Number 8, let's do this one together. So I now have a negative charge, which means I need to switch to the left-hand rule. So I'm going to take my pistol roll, and I'm going to use the index finger going in the direction of velocity, rotate my wrist so that my bird finger is out of the paper. So velocity is pointed in the northwest direction. My bird finger is pointed out of the paper, and my thumb is going to point perpendicular to all of this. So I'm going to have pointing at either 225 degrees, you could write that, or you could say southwest. Now, just a quick reminder, I know some of you are using the palm rule instead of the pistol rule. You can do all of these with the palm rule as well, and you should get the exact same results. If you're having any trouble with this part, and it can be the hardest part for people is figuring these out, just send me an email. We'll try to set up a FaceTime or some way for me to help you with doing these. So next up for this lecture is the magnetic force in a proton. So a beam of protons, and they give you the charge, moves at 3 times 10 to the 5th meters per second through a uniform 2 Tesla magnetic field directed along the positive z-axis. The velocity of each proton lies in the xz plane and is directed 30 degrees to the x-axis. Find the force on the proton. So the easiest way to approach this is just to say QV times B times sine of the angle between. So if you plug your numbers in, you're going to get 1.6 e negative 19 times your velocity, which is 3e5, times your magnetic field, which is 2, times, and I'm sorry, I have to write on the next line here, times sine of 30 degrees, which is the angle between those two. When you do that, you should get 4.8 times 10 to the negative 14th newtons. Now, how do I get the direction? Because they didn't just say magnitude, they said the direction. So what you also need to do is use your pistol rule, and it's a right-hand pistol rule. So you're going to put your index finger in one direction, and you're going to put your magnetic field, your bird finger in that direction. And with what I'm looking at, I end up getting that it's going in the negative j-hat direction. So it's actually headed down that way, so the negative y direction. And we're done with that problem. Okay, we're going to talk about magnetic flux and magnetic field lines. Just, a quick reminder that magnetic field lines are not lines of force. So if you take the magnetic field lines, you can see they show basically which way a compass would point at each of these points. And magnetic field lines always point away. They always point away from the North Pole. And magnetic field lines always point towards the South Pole. But one thing to keep in mind is the magnetic field lines are not the direction of the force. The force is going to be perpendicular to the direction of the magnetic field lines. So that's kind of our big takeaway for this. So this is just a nice illustration of where students might go wrong. So make sure that you understand that the force is not in the direction of the magnetic field, but this is correct. This is the correct one. So it's the magnetic field will always be perpendicular to the force, and the force will be perpendicular to the velocity. That leads us to Gauss's law of magnetism. And Gauss's law, I know, is challenging for electricity, but it's much easier for magnetism. So the situation with electricity, which I'll show you kind of on the side here, is we'd have a Gaussian surface, and then however much charge was enclosed would indicate how much flux was in there. So that's really our Gauss's law of electricity. But magnetism, since you always have a North Pole and a South Pole, you end up with a situation where the amount of flux lines coming in, if I draw my Gaussian surface, the amount of flux lines coming in is always counterbalanced by the amount of flux lines coming out. So in this case, the closed path integral of B dot dA through any Gaussian surface will always be equal to 0. That's because the amount of flux lines coming in will always be balanced by the flux lines coming out. So this is the part we're worried about right now. I will be talking to you about Ampere's law a little later. But for right now, we don't have to worry about this section. We can just ignore this section for right now. In the previous video, they talked to you about how to calculate flux, but I'm just going to take you through a calculation and take you through the units. The units for flux, if we're talking about, the integral, so flux by definition, magnetic flux is basically how many field lines are passing, or how much field lines is passing through an area. We can typically get away with just doing the dot product of the B dotted with the A, so long as the B is constant, which means you basically are taking the magnetic field magnitude times the area magnitude times, now this gets a little tricky, the cosine of the angle between the area vector and the magnetic field vector. So what you're going to end up doing in this case is you're going to calculate your magnetic flux. Just a quick comment on units. The units we're going to be working with are going to be the units for magnetic field, which is Tesla, times the units for area, which is meters squared, and that's actually our unit of Weber. So 1 Weber. So 1 Tesla meter squared is 1 Weber. So if you see units like that, that's what we're working with. In this case, so we have a perspective of a flat surface with area 3 centimeters squared. Be a little careful. 3 centimeters squared actually converts when you square it, not to moving the decimal 2 places, but to actually moving the decimal 4 places. So I'm going to end up saying that 1 centimeter squared is going to be the same as 1 times 10 to the negative 4th meter squared. So this is going to be 3 times 10 to the negative 4th meters squared. And then the flux they gave us here was equal to 0.9, and it's milliweber, so E negative 3 Webers. And so basically all we have to do is use this equation. We use a rearrangement of this equation. We're going to take the flux, and we're going to divide by the area, and we're going to divide by cosine 60. So let's talk about that cosine 60 for a second. What's going on here is that your area vector is always going to be perpendicular to your surface. So if this is my area surface, so when you look through this, basically you have to pay attention to the fact that the area vector is perpendicular to the surface. And so if you set that up, you recognize there's an angle of 30 degrees, which means the angle between the B field and the area vector is actually 60 degrees. So you're going to end up with cosine 60. So the confusing point here is just remembering that when you have an area, that the area vector is always going to be perpendicular to that surface. So keep that in mind. Last but not least, we're going to talk about what happens when charges go into magnetic fields. So this is kind of neat. We're going to be looking at the cyclotron equation. So if I have a positive charge that's entering in here, and it's got a velocity v, you're going to use your pistol rule or your palm rule, and I want you to figure out which way the force is going to be on this. So pause the video for a second and think about which way your force is going to be on this. Since it's a positive charge, I think we can see that the force is going to be pointed that way, which means my object will take a path that looks like this. So I have a positive charge here and I have a velocity vector going this way. Again, use your pistol rule. Which way is the force going to point? I think you can see, if you work through it, that the force will point towards the center. And then we keep going around and we get up to here, and I draw on my positive charge again, which has a velocity v. And you might be noticing that this magnetic force is exerting a centripetal force. So we can continue going around, and you can check each point, and you can see that it's going to be pointing towards the center at each point, which provides us some kind of really important information. When we think about what fields do, electric fields tend to accelerate things tangentially. So they speed them up and they slow them down. But what do magnetic fields do? Magnetic fields are useful because they can accelerate things centripetally. So if you want a centripetal acceleration, you're going to use a magnetic field. If you want a tangential acceleration, speeding up or slowing down, you're going to use an electric field. So let's put this all together, and we're going to set our magnetic force equal to our centripetal force. So I'm going to write out the equation for this. It's going to be QVB, and we're going to assume sine 90, is equal to mv squared over r. And you are responsible for being able to derive this. So when I do this, I'm going to get mv squared over r. The v's are going to cancel. The sine 90 is just 1. And when you rearrange, let's make our r actually a capital R. When you rearrange this equation, you're going to get that r is mv over qb, which is known as the cyclotron equation. Okay. So this has all kinds of really unique applications. One is you can take an electron beam, and when we get back to class, we'll actually be able to do this in lab. We can take an electron beam, we can bend it into a circle using a Helmholtz coil. That's the picture that you see right here. We can also take a charged particle, and if we have a little bit of an initial velocity with that particle can actually move in a helix. So instead of just getting a flat circle like we got above, we can get a helix. Okay, and this picture 27.19 is a magnetic bottle. So particles near either end of the region experience a magnetic force towards the center of the region. This is one way of containing an ionized gas that has a temperature on the order of 10 to the 6 Kelvin, which would vaporize any material container. So in a sense, we actually use this approach to keep things under that are very, very hot in a safe zone, the magnetic field. The last thing I'm going to look at today is just an example problem. So you have a magnetron in a microwave of an emitting electromagnetic waves with frequency of 2450 megahertz. Okay, so we need to figure out what does that mean for our magnetic field. Okay, we know it's an electron. So with an electron, we know that our mass is going to be 9.11 times 10 to the negative 31 kilograms. We know that the magnitude of our charge is going to be 1.6 times 10 to the negative 19 coulombs. So we need to think about our path. So we have R equals mv over qb. But we also know that if we rearrange things a little bit for this and try to solve for b, I can rearrange and say that b is going to be m times v over q times r. And some of you might remember that this v over r is simply Wombo. So m over q times Wombo. And Wombo we can get because Wombo is 2 pi times the frequency that we have. So if you plug in those numbers as they did up here, you will find out that you get 0.0877 Tesla. Thank you so much, and feel free to email me with any questions, concerns, or feedback about this video.